Okay, so now we will have another example. Okay, to be exact, this will be our fifth example for the topic strain. Okay, so the timber, okay, so this will be our problem 2.12. So the timber member has a cross-sectional area of 1750 mm squared and its modulus of elasticity is 12 gigapascal. So compute the change in the total length of the member after the loads are applied. Okay, so without further ado, we'll go directly into the solution. Okay, so here is our solution. Okay, so I just copied the figure. Okay, so one thing we should do is to divide um, the whole timber, okay, into three portions. So since it has A, B, C, and D, and it has three forces, so let us do some type of divide and conquer. Okay, into which, okay, so the first thing we should do is to concentrate at the free end. So since it has a 20 kilonewton tension, so we got 20 kilonewton tension here and a counteracting balancing force of 20 kilonewton at the other side. Okay, so by looking upon the inside, okay, so we go from outside to inside. So outside 20, 20. So at inside, it is 35 going to that direction, inward. Okay, so since this is 20 kilonewton inward, so this should be 15 kilonewton inward. So it will result to 35. So 15 inward. So since it is inward, so it is 15 kilonewton compression. Unlike here, tension. So 15 kilonewton compression here. So 15 kilonewton compression here, or both inwards. So by looking again at the graph, so therefore it is 15 kilonewton. It's supposed to be 15 kilonewton here. In order to become 40, it should be added to 25. Same direction since it is 15 kilonewton inward and this is 40 kilonewton inward. So in order that to become 40 kilonewton inward, this another portion from AB should be 25 kilonewton outward. Okay, outward, left 15 left, so it will become I mean 25 kilonewton right, 15 kilonewton right. If you add them, it will become 40 kilonewton right. So therefore 25 kilonewton at AB is tension, at BC 15 kilonewton compression, at portion CD is 20 kilonewton tension. Okay, so please take note that tension and compression should have not the same sign convention. Okay, so the most common is that we will use, in order that we will not be bewildered, is tension is positive, compression is negative. So therefore, okay, so please take note of that. So the total change in length, or the deformation, is just the summation of all of the deformations of each portion A, B, B, C, and C, D. So it is the summation of PL over EA, or the equation for deformation. Here, PL over AA of AB, PL over AA for of BC, and PL over EA for CD. Okay, so here we are, the next portion of our solution. So as you can see, okay, 25 kilonewton times 10 to the third Newton. Okay, so I convert it to Newton. And then 1.5 times 10 to the third mm. So I convert the length of AB to mm. And then I convert the modulus of elasticity, which is 12 gigapascals, into Newton per mm squared. In order that 1 gigapascal will be converted into Newton per mm squared, okay? Okay, in order that 12 gigapascal, a gigapascal is converted into Newton mm squared, you just multiply it by 1000 or 10 to the power of 3 over the area. The area is uniform 1750 mm squared. Okay, so we apply all the force respectively. PL over EA, 1 by 1. Okay. Take note of the lengths, 3 meters and 3 meters. Both 3 meters for BC and CD. So, PL over EA converted all the forces into Newton and all the lengths into mm in order that all will be uniform. Okay? So, please take note that if the force is tension, it's positive. If the force is compression, it's negative. Okay? So that's why 15 here is compression, so negative. So therefore, to make the long story short, the computed total deformation is 2.50 mm. Okay? So I hope you understand this example.